to process, which is quite time-consuming and labor-intensive. And also, reconstructions done by different persons could be different because of their subjectivities. So these issues of time, labor, and subjectivity are inhibiting investigators from solving crimes efficiently. So in collaboration with forensic specialists in the nationally renowned forensic labs in US, our team is building a digital skull restoration and facial reconstruction pipeline, as we listed here, to make this whole procedure more efficient and more objective. I will go over all multiple steps here to explain what we're doing. So the first step is the fragmented skull reassembly. The first thing we are looking at are the bones themselves. When the bones come to us, the skulls are usually fragmented with part of them missing, often damaged by animals or environmental activities. So the first step is to reassemble these pieces back to their original geometry. And conventionally, fragmented pieces need to be manually reassembled and glued together using wax or other glue materials like this. So this again is slow and dependent on the modeler's skill. So in our platform, we first 3D scan the fragments into digital models. And then we have our computers to do the reassembly for us. Okay, but the challenge here is how do we teach computers to reassemble these fragments automatically? If we consider the reassembly problem in 2D, this is equivalent to teaching computers to solve jigsaw puzzles. Although this has been studied in AI and the computer vision fields for more than 2 decades, we found that many existing algorithms only work on toy examples and couldn't handle moderately complex puzzles. But why is this difficult? The key to the effective stitching of fragmented pieces is actually closely related to the registration and reconstruction techniques that we are familiar in computer vision fields. So basically, we need to first compute correspondence between fragments, and then we can use this correspondence to help us stitch these pieces together into a global model. Feature modeling has been extensively studied in computer vision fields. Many key point detectors and many feature descriptors have been studied and developed for both 2D and 3D visual data. Our group has also been working on feature extraction and modeling from images and geometric data in different tasks. We developed quite a few feature detectors, descriptors, and corresponding matching solvers. But I'm not going into the design details here. But directly applying all these techniques to solve jigsaw puzzles still remains challenging. And this is because unlike the common registration and reconstruction problem, a fragment reassembly can be considered as a extremal case of the white baseline matching problem. So for example, look at the pictures on the right. As we know, when we do matching, if the images only undergo small transformation, small shift, or they have a big overlap between each other, then their registration and matching can be easily computed, obviously. But if the two relevant images share small overlap and the matching patterns become weaker, then they are harder to register. And now we are dealing with fragments where adjacent pieces only barely touch each other. We should assume that there's no clear overlap, and also the consistency on the geometry and textures between adjacent pieces are weak and sometimes ambiguous. So we can assume that the matching or correspondence can be computed, but they are often unreliable. So our general strategy is to solve this problem through a 2-step pipeline. We first compute pairwise matching. We compute redundant matchings. So basically, between any 2 pair of pieces, we compute as many as possible potential matches, and they form a dense correlation network like this. So such a network can be it's not a simple graph. It could be a multi-graph, meaning between two fragments, between two pieces or two nodes, there could be multiple alignments calculated. Okay. Then we do a global composition where we try to prune the graph, enforcing a certain type of local or global consistency constraints to find a final simple graph that maximize the matching scores. So basically, starting from the multi-graph, we prune it, enforcing some global constraints, and then obtain a final simplified graph. For example, we can incorporate certain constraints like co-cycle, transition coherency, or loop closure. These are all common constraints used in like a SLAM literature, and we use this to enforce basically the two adjacent pieces when we require them. Not only that they are well aligned, but also when we consider multiple pieces together, they should be able to compose consistently. Okay, I'll skip these technical details. But the intuition is like we can start with a complicated multi-graph, and then we can simplify it by enforcing some compositions and get the reassembly more reliably. And we have developed multiple global composition solvers, allowing us to effectively solve various global composition problems. So with this development, with our learned features and composition solvers, we are able to solve puzzles with hundreds of pieces. Like for example, such a small, small piece, a puzzle with many pieces, small pieces, we'll be able to reassemble them. And this significantly enhanced the effectiveness of the fragment reassembly. So these are 2D examples. And our system also works with 3D objects. Oh, I saw there's a delay. Sorry, there's a video I'm trying to play. So we have this 3D models. We break it into pieces, and then we scan them. Okay, and our system can recompose them. Let me try to optimize for video, so there's no delay. Okay. So these are some other examples. Another example. On real skulls, this pipeline also works. And this is an example that our program reassemble a fragmented skull. This is another skull example. So after fragment reassembly, the restored skulls are often incomplete. So here, in this case, these regions of the skull were damaged by a gunshot, and those pieces were not found. So we need a program to help us repair this damaged region and restore the complete skull. So we go to the next step, the skull restoration, the completion. We developed a skull completion system. So basically, this is a 3D impending problem. We developed several strategies. We can use the symmetry. For example, the skull, we can use the right side to repair the left side, as our human skulls are generally symmetric. We can also do a template. We can also transplanting a template model and copy the counterpart from the standard template and deform it a little bit to match the missing region. We can also we can also better complete the geometry of the missing part by using a statistical model built upon a skull database. Okay. Sorry, so there's a delay in this slides. So we integrate all these 3 strategies and build a reliable repairing system for damaged skulls. Okay. After the skull is reassembled and repaired, it's often easier for us to detect the so-called physiological landmarks on the skull. And these landmarks are very useful in many subsequent skull and face modeling tasks. So I will very briefly talk about the landmark detection in skulls. Okay, specifically, given a skull, what we want to do is to detect a set of physiological landmarks like this, that they are either anatomically important or geometrically salient, and they serve as feature points or anchor points in many subsequent modeling and analysis tasks. So this is closely related to facial landmark detection, actually. Facial landmark detection, both on either 2D face images or on 3D face scans, have been extensively studied, and they often can be handled reliably. Oh, and another closely related and widely studied problem is the 3D human pose estimation, 2D human, 3D human pose estimation, which detect the skeleton and joints on images or depth images or videos. While all these techniques are closely related and have been well studied, for 3D skulls, however, they cannot be directly applied. The key issue is the lack of annotated data sets, because no many skull data sets are available, and their annotations are even fewer. So for 3D skulls, very few tools are landmark detection tools are available. There are a few geometric methods that have been developed. For example, people use deformable reference templates or active appearance models to fit the template and localize the landmarks. Some convert the 3D data onto 2D images and then apply 2D landmark detection methods. There are also a few relevant neural network regression systems that could be applied. But in general, again, because of the lack of well-annotated data, this has been little explored. So recently we built an end-to-end 3D detection network that extracts and combines both global and local feature extracted from the skull and face pairs to regress the landmarks on skull and face simultaneously. So with this, we can flexibly identify various landmarks on skulls and faces. Since this landmark detection is a separate and general topic, in the interest of time, I will skip this part in this tutorial. So with a restored skull, we also often do a skull classification before we perform the subsequent the face reconstruction. So by skull classification, I mean, given the skull, we want to identify its biological profile, such as race, sex, age, and so on. Right, so input the skull, we try to detect what's its race, what's its sex, and age information, and so on. So this is classification. Classification is also well explored in computer vision literature. But again, in terms of skull classification, because of the limited availability of public skull data, classification tools need to be built differently. So rather than directly training a model that learns everything from scratch, most existing skull classification algorithms adopt or learn certain prior knowledges. So they learn to use some so-called anthroposcopic traits. So for example, these are some illustrated figures. Some conventional traits are like measuring the distance between some landmarks. We just talked about landmark detection. So measure distance between landmarks on the skull, or use the geometric shapes of certain regions of the skulls. And these are oftentimes traits that can be used to classify the skull. So also again, since classification problem is also well studied, and we will not dig into this about this task. I'll just list a few work. The 4-disc, the first one, has been widely used by forensic scientists. We also developed a classification system, the second one, that integrates the palette shapes into classification to make the classification accuracy better. I also list some recent surveys on this work. In any case, skull classification, if we could have plenty of data, then this is nothing special. And we just incorporate certain features and then use them to build the system. Okay, then I would like to move to the next step, the face creation task, which is probably more fun. With the skull restored and classified, we now have a complete model. We have landmark defined on that. And now we move to the next step to create the face upon the skull. Performing an accurate facial reconstruction from the skull is actually quite challenging, even for forensic specialists. In forensic labs, to reconstruct the face from the skull, the modelers oftentimes first place a set of landmarks like this, shown in the middle, on the skull, and then they trim their length to mimic the average tissue thickness, and then use them to constrain the face geometry to be constructed on the skull. So although the general geometry of the face can be mostly determined by the skull and the tissue depth, while certain features such as lip shapes, eyebrows, etc., cannot be inferred directly from the skull. And therefore, a realistic facial reconstruction often need to rely on certain artistic interpretation from the modelers. So this is how they do it manually. Using computers, if we want to tackle this under constraint synthesis problem, so under constraint meaning that given the skull and some tissue depth information, there could be more than one possible face. Current technologies are mainly based on either computer graphics methods or statistical-based models. Both of them use geometries from the skull and the tissue information to infer the facial structure and the geometry. Many pure graphics and geometry-based methods use deformable templates to match the landmarks extended from the skull, and some of them apply certain smoothness regularizations. So this often leads to less accurate geometric alignments with the skull, or unrealistic, or we may have unrealistic artifacts in the in some reconstructed regions on the face. On the other hand, in another categories, there are quite a few face reconstruction methods that are built directly through statistical regression. So here are a few work. A common limitation for this method is that they train a statistical model that regress the results directly. If the model was trained on one data set, mainly containing one ancestry, then when we apply this to a skull from a different category, or like from a different bioprofile category, then the performance drops significantly. And another issue for this statistic method is the loss of detail, as it tends to generate smooth results. So many facial geometric details is smoothed out. So we developed a different pipeline to tackle this under constraint problem. Because it's under constraint, instead of directly reconstruct a face from the skull, we first reconstruct candidate faces using face images. Okay, reconstruct the 3D face from an image is much easier, and this can produce more realistic and detailed face to start with. So we can download photos from internet, or we can get photos from the database of missing persons. Then we have a large amount of face candidates. So after we reconstruct the 3D faces, we can perform a superimposition to match the query skull with each of these 3D faces. We can easily see how likely the skull match with this 3D face. Then we can pick the top candidate and use this superimposition to help us further refine the reconstructed face. So let's look at the first step of this pipeline, 3D face reconstruction from a portrait image. So the input is a portrait photo and the output is a 3D face. So we built this pipeline. We adopt the parametric face model, which is the decoder here. We could use, for example, a FLAM model or the more recent data model or other models. So they usually describe a 3D face using parameters describing, say, geometric shapes, face pose, and expressions, and so on. And we call such a parameters semantic code or semantic vector. And then we train a encoder using a deep convolutional neural network. We train such an encoder to map a given photo into semantic code. And this encoder and decoder network can be trained in a self-supervised way. So after we get starting from an image, we encode it into a vector, we decode it into a 3D face, and we render it to generate a new picture. And then we extract the landmarks on these pictures. We can compare this picture with the given input portrait and use this to refine both the encoder and, if needed, also the decoder. Okay, so that's the general pipeline. To support this training, we integrate multiple face database from internet. We built a big, consistently parameterized face database. So this database will have a 3D face together with its 2D pictures. So we collect all these public available 3D face data sets, which each of them contains a few thousand 3D faces. But different databases have different sampling resolution and tessellations. So we register all these faces and fuse them together to build a consistently sampled face data sets. So basically, we need 3D face because we want to retrain the decoder, so it covers different type of people from different ancestries. So after we built this unified data set, we get about 35,000 3D faces. All of them are associated with 2D images. They cover different ancestries, like some are European, some African, some Asians, and they have males and females. Okay, so we can use this to train our decoders, and then also use them to train the encoders for the image to face reconstruction. Another issue is that the 3D face reconstruction results is often affected by the used portrait photo. So a same person's different portraits may lead to different 3D face geometries if we use different photos. And to make this procedure more stable and robust, we can make use of multiple photos coming from the same person. Then we can enforce the reconstruction to converge to a similar geometric parameters. Okay, then with this, we'll be able to get a more stable 3D reconstruction. So this shows some examples. We use multiple photos of the same person, asking the geometry to be similar, and then the results will be more stable. Okay, so here are some results in comparison with other reconstruction methods. We can see that our produced face look realistic, and they contain good detail. These are some quantitative comparisons. You can also see that our methods produce faces with smaller reconstruction errors. Okay. So with this system, we can now do the facial reconstruction from a portrait image. Given any photo we found online, we'll be able to reconstruct its corresponding 3D face geometries like this. Then we do the second step, the superimposition. So basically, given a skull and a 3D face, we want to compare, we want to match them and see how likely they belong to the same person. So to do this superimposition, we just check following a set of tissue depths defined on landmarks, how well the skull matches with the face structure. For example, so we first fit the face onto the skull, and then between the corresponding skull landmarks and facial landmarks, we measure the distance. If this distance is close to the mean tissue depth, then we consider this as a normal region. We put the green points. And then otherwise, if the tissue depth is outside the normal range, then we consider this region to be not well matched. We put the red points here. Eventually, we calculate the matching score using the ratio between the red and green and red points. Okay. Now with this scheme, we will be able to calculate the similarity score between the query skull and all the 3D face we reconstructed. Okay, so we can tell which 3D face might be a good candidate for this query skull. Okay, then finally, with that candidate selected, we can do a face resynthesis. We know that through the superimposition, we know which region of the face matches well with the skull, but some other regions might not be well matched. So we want to modify those regions according to the landmarks extended from the skull. So basically here, we try to perform a plastic surgery to modify those unmatched region and until those regions now can pass the landmark extended from the skull. Okay. To do this, we built a geometry constraint generative adversarial network. So GCGAN. So the generator G takes in a Gaussian noise Z and a landmark vector, a landmark extended from the skull, and then map them to the semantic code C. And this C can be decoded into a 3D face. The discriminator D checks this generated face to see if it is realistic and see if it aligns well with the skull by checking if it passed extended landmarks. So if not, then D will reject this face. So this is the simple design of this pipeline. Okay, with this we can see that given a top candidate, we perform such kind of face modification, and after the modification, some originally red region, unmatched region, now become aligns well with the skull. And this gives us the final face reconstruction. Okay, we also tested that the reconstruction from different candidates could result in different final faces. So as we said, this is an under constraint problem. So given the skull together with the tissue depth, we might be able to generate multiple faces. So let me play the video. So we can see that given the input skull and the defined tissue depth, now we have two candidates. The initial geometry are quite different. In the first row, the second and the fourth figure shows the original geometry. They are very different. After the modification, the resultant geometry looks quite similar to each other, but there are still some difference. And from the landmarks, the landmark errors are both already very small. Okay. If we apply the texture, the final face will obviously look much more different. Okay, play that. Geometry is similar, but yeah, obviously after the texture is applied, they're very different. Okay, we also evaluate the accuracy of our reconstruction using real data. We collected many 3D CT scans, and from which we can extract the skull geometry and the face geometry. So then extracted face can be used as the ground truth. So given a skull, we first still go through the pipeline. We pick some initial face candidates from our portrait database downloaded from internet. Then we get this initial face reconstructed, as we can see in the third column. Then after the modification, we get the final face. The final face now is compared with the ground truth face G. And then we calculate their point-wise error. Okay, so here are some more examples. The reconstruction error in these bright regions are around 2.5 to 3 millimeters. We have so far collected about 280 scans, and we randomly selected 100 to perform the testing experiments. These are the plot of the rooted mean square errors. So 80% of the reconstructed faces have are messy rooted mean square error smaller than 2.5 millimeters. 99% have of them are smaller than 3.5 millimeters. So comparing with other existing work, skull to face reconstruction methods, our reconstruction error is significantly smaller. Okay. Another issue, as we said, this is an under constraint problem. So also the tissue thickness we used is following the forensic specialist we use is the static means. But this does not capture the full range of the fatness levels. So basically like tissue depths, it could be like a thicker or be thinner, indicating different fatness levels. In order to explore different plausible faces, we also enumerate different tissue thickness, so that we can allow the users to see different type of faces under different fatness level. To do this, we train a regression network, suppose we call it as R, and we use this R to model the correlations between different tissue thickness on different landmarks. So this network will take in a delta tissue depth. Like on some regions, we might adjust or perturb the tissue depth, and then this network will output the most likely distribution of the tissue depth on the other regions. Okay, so maybe it's easier to show this on this demo. So this demo. So starting from a current face, we adjust the tissue depth at the left cheek. So then we apply this network. It will calculate the distribution, the tissue distribution on all the other landmarks. Okay, and then it will adjust the face accordingly. Now we can see that the face becomes rounder, bigger, fatter. And then we also can apply some tissue adjustment on the nose region, increase those tissue depths, and all the other tissue depths will be automatically adjust accordingly. Now we'll get a new face where the nose region grows. Okay. So basically, we show that we can effectively allow the users to adjust one or two tissue depths, and then propagate this to the other face regions, and then we'll be able to explore the face space. Okay. Okay. So this shows our whole pipeline. So this is, I went over this digital skull restoration and face reconstruction pipeline, which involves multiple skull and face modeling tasks. I also briefly discussed their relevant computer vision techniques. And obviously, many of these techniques are general and can be used in many other computer vision tasks. So for example, our reassembly and restoration techniques can be used to restore archaeological relics So here we have actually built such an acquisition system and deployed it in Armenia in last summer, helping anthropologists digitize and restore hundreds of shirts during their work days. And we also developed digital unshredder, which helps us restore the shredded documents. We can also apply this to perform the matching algorithm to perform low bandwidth SLAM or 3D reconstruction from sparse coverage. So it's like solving a jigsaw puzzle. If we have pictures captured in the scene, but they are only sparsely covering the scene, the overlap between adjacent pieces are very small, or adjacent frames are very small, overlap is small, then we can still restore and reconstruct the scene. Okay. We are also working on aging and de-aging of the face so that we can do a missing person identification or missing children identification, face editing. So these are some relevant applications. Some ongoing research directions or challenges. In order to train more powerful, reliable craniofacial modeling on analysis tools, one challenge is the lack of data, as we said. Okay, we don't have good annotated skull or face data, so we need more efficient acquisition systems. And actually, in the next tutorial, Dr. Xu will talk about their acquisition system, which is very powerful. And so that's one thing. Also, to support convenient and more semantically controllable face editing, and also face enumeration, we need more effective trace decoupling techniques so we can build a better latent space for the face for us to explore. Okay, so I think this is mainly what we worked on the skull restoration and face modeling. I would like to thank my collaborators and my students and also the funding agencies. For more details, please feel free to check my webpage. And if you have questions, I'm happy to take questions here, or you can contact me by email. Okay. That's it. So.
Hello, I don't know if you can hear me. Can you hear me?
Yes. Mm-hmm.
Yes. Sorry, I raised my hand, but I don't know if you guys are looking at that. Great work. Pretty amazing pipelines that you presented. I'm quite happy to have been able to make the workshop. I would like to ask about the part where you evaluate using real CT data. And the question is, how did you do the registration between the reconstruction and the CT scan? And what type of transformation are you using? Is it just a Euclidean rotation, translation, and scale, or is there any more parameters on that transformation?
Oh yeah, so I think all the skulls and the face are pre-processed, are transformed into a canonical coordinate system. Like it's called a Frankfurt coordinate system. So yeah, they are all normalized into a same coordinate system and measured under that environment. Yeah.
Okay, that's good that's good to know. Then I mean, you might be able to get slightly smaller errors, because there seems to be in some of your images the error display images, it seems like, say, half the face has more error than the other half, and that's typically the result of a misregistration. So just so that you know, and just bring it to your attention, you might be able to get even smaller errors if you do the registration. I don't know.
Non-rigid. Yeah.
I don't know how to say better, but better, you know.
That's right.
Your algorithm might be misjudged. But well done. Yeah. Very well done. Nicely done. Thank you.
I see. Yeah. Thanks. Mhm. Okay. So so if there's no more questions, I guess I can pass this to the our next presenter.
Sorry,
And
if
we'll
that's
stop here.
if no one's asking any other questions, may I ask a question about runtime?
Oh, sure. Mhm.
Is that okay? How long does it take to get that initial phase from a single picture? What's a runtime?
Oh, so runtime. I don't have this number immediately with me. I don't think it's quick. I don't think it's slow. Reconstruction. This basically just let's see. It's just the decoding.
That's right.
I think yeah.
But
It's
could
very
you do it?
quick.
Could you
And
do it
also
real
this
time,
is a
like 30
offline
frames a
actually.
second? Pardon me?
30 frames per second. Sorry, yeah, and also this is done during an offline stage. This is basically like we have this database, and then we pre-calculate all the 3D faces and save them. And then now whenever we have a query scout, we just basically do the superimposition to pick the candidate. So this doesn't need to be very quick, right? 30 frames per second. I don't
in the
think it's that
context
quick.
of no,
But,
okay.
Right.
Right.
Yeah.
So in the context of reconstructing and doing the fit to skull and such, that certainly doesn't seem like it would require real-time speeds. But I was wondering for, alternative uses that you could give your algorithm. 30 frames a second would probably be standard video
Nice.
speed.
Right. I don't remember it's that quick, but
okay.
Yeah.
Sounds good. Thank you so much.
Thanks. Okay. Then I guess I'll stop sharing, and then yeah, Dr. Shi will and I didn't check the time.
Yeah, I think yeah, that's right. Yeah, but shall we directly go on my talk? Yeah. Or yeah. Shall we take a 5-minute break, or shall we just start? Right.
Either way would work. Let's see. Maybe we can. So I think it's now 20. I don't know. Maybe we can start directly.
Yeah. Okay. Yeah.
Yeah, if the audience don't mind.
Okay. Hi, Professor Lee. Could you see the screen?
Yes, I can see it. Yeah,
great. Yeah. And yeah, thanks for the invitation and thanks for the nice talk. And I will continue the topics about facial modeling from the inner and outer modeling into the dynamic facial scanning, and especially for facial performance capture. And my talk will start. Actually, I will cover several aspects from data capture to different kind of ongoing research directions in my group. And first, I would like to introduce several live field devices for facial modeling. And actually, in Shanghai Tech here, we maintain various live field devices. Actually, this kind of live field device, in these devices, we use different kind of lighting conditionings and which is combination with different kind of camera settings, so as to capture different, outer facial attributes of different performance. Yeah, and I will provide several examples about how we capture the facial data and how we use this kind of data to perform some data-driven facial asset generation or creation tasks. And For the first version about the such live field device, I would like to introduce the photometric stereo systems for facial detail synthesis. In these systems, we use the photometric stereo techniques to capture several images under different lighting conditions about the performer. Then we could recover the fine-grained details about the facial geometries. And especially we use different view angles to capture the RGB images. And based on these images, we could recover the basic geometries from the multi-view stereos, and the photometric stereos provides additional geometry details on top of the policy provided by the MVS. And actually, based on this kind of facial geometries, what we would like to do is we want to further reconstruct the geometries from several more lightweight inputs, for example, such as an images. If we could collect a large data set from our photometric stereo systems, and then maybe we could, based on our data set, we could do some tasks like facial detail synthesis from images input. So actually, our techniques, in a nutshell, our techniques employs the expression analysis to attain a high quality process or prior for the facial geometries, and then we combine the facial geometry details from in terms of the bond map or in the UV space. Yeah, and actually we apply in our systems. Yeah, it's a paper in ICCV several years ago, and based on the data that we capture using the photometric stereos, we develop a networks called deep facial detail network. It contains two cascade UNet modules, one for partial detail inference, and then one for partial detail refinement. And these two modules work cascadely. Yeah, and we also combine the supervised and unsupervised learnings into a conditional gain pipeline actually to combine the facial geometry details captured in our light stage systems, and also we would like to generalize it to various images input. So we do it in a hybrid way, in combining the supervised learning and the unsupervised learning. And for the data sets, actually we contribute our data set from the light stage systems. Actually, it was like a small scale light stage, which is in conjunction with multi-view stereo. The multi-view stereos allow us to correct the perspective distortions, especially with the near light source, and at the same time capture the high quality details through the photometric stereos. And actually, we capture about 400 high quality 3D scans for about 120 identities under several different facial expressions. And we also augment our training data with available data sets, for example, from the one, including the one from ICT. Yeah. And actually, we also train the network we also slice in the images input and the output displacements, because the slicing means we only apply our UNet locally. We use the local patches at about 256 resolution to enhance our network generalizations. And we model the displacements not directly in the pixel space, but under the PCA space, where each patch is a linear combinations of 64 basis patches. And using this kind of slicing networks, we could finally output a high resolution displacement map, yeah, so as to recover enough fine-grained geometry details. Yeah, and here we are going to show some results. After training from a single photo of Robin Williams, we managed to recover very realistic 3D face, especially for the geometry details. And in these photos, actually it's quite difficult because Jack Ma and Donald Trump show different expressions, especially under very different lighting conditions. Yet our method still can recover very high quality facial geometries, despite their strong difference in terms of expressions or lighting conditions. Yeah, and in this example, we show how to recover the facial geometries and then use the facial geometry details to train a network to predict the high quality facial geometry details from RGB images input. And actually the live view device could do more. And not only for facial geometry reconstruction, it's also very useful to provide high quality data for facial relighting. Here I'm going to show another system called in another live view device and live view systems, which is used to capture, sorry for the noise. Yeah, it's used to capture the OLED image, or called one light at a time. At each time frame, only a single light is on. So we use the high-speed cameras to capture all these OLED images from the same viewpoint, but under different light on. So once we have the OLED images, we could linearly combine them into these OLED images slots into a relighting one, which is fit the foreground portraits into various background environment map with different lighting conditions. For example, like a moving car under the street lights at night. And this kind of OLED images provides diverse and various facial relighting data. This data is super important for facial capturing and especially for facial or portrait relighting. So actually we show an example to how to use this kind of OLED data. In this where we use this kind of live view OLED data to train a network called video portrait relighting. Actually, because we use the high-speed cameras, and the high-speed cameras provides high quality, high quality free view, high quality video data for the OLED shots. So finally, in this world, we managed to train a network which could provide a portrait relighting video version of portrait relighting. Actually, in real time, it could be run in a mobile device or in a laptop. Yeah. Here, let's see the demo first.
Temporal and lighting consistency to enable realistic video portrait light editing, whilst maintaining real-time performance even on portable device.
Yeah, it could generalize to different identities by different video inputs, and we could relate the videos into different background environment map. And actually, the network itself is super lightweight, so it could be run super highly efficiently for portrait relighting. Actually, the whole network actually works as a super lightweight unit only. Yeah, we take an images input and then we use an decoder to output the released version. And very differently, we use the semantic outputs to disentanglement, to provide extra portrait structure informations. And we also, because we have the temporal information in our OLED data, so we managed to use the flow-based temporal modelings in the adversarial training network. Yeah. And because the network is super lightweight, so it could be easily to be embedded into any laptop or even mobile phone. In this example, we show how we could edit the lighting conditionings for arbitrary portrait images or videos. Yeah, we even made a small app run on the phone, and then people could select an images and change the lighting conditions, like provides extra light or delete the light or changing the lighting conditions. Yeah, and actually all the benefits comes from the data, I would say, because the network itself is super efficient, I would say. Yeah, but actually the live view device provides sufficient relatable data from the OLED videos actually. So I'm going to show another examples called that combines the photometric stereos with the multi-view stereo systems. It combines the relighting abilities and the geometry abilities all together to provide facial asset generation abilities. Actually, we use it to correct the, oh, sorry. Actually, we use it to correct the physically based rendering for physically based assets. I would discuss about the physically based later, but actually in these systems, we could provide 3D visual scans and 4D visual scans to capture the dynamic animations or visual captures about the performance. And after we managed to handle all this kind of data, once we have the physically based textures about the performance, we could recover the diffusions, the speculators, the normals, and the visual details. Yeah, and because it's physically based rendering, so we could relate it directly into different kind of backgrounds. Yeah, and here I'm going to show because actually it supports physically based rendering, so it natively supports look depth. Yeah, so here we show rendering results and the real and compared to the real images. Actually, the lighting conditions, actually we could see how the light shading on the facial regions is kind of difficult to distinguish the real one and the rendering one, especially according to the shadow movements across the facial regions. Yeah, and here we compare the geometry reconstruction abilities about this kind of live view devices compared to previous multi-view stereos. Actually, please notice the live view scans could capture much stronger facial geometry details compared to traditional multi-view images. This kind of geometry details actually comes from the photometric stereos or the lighting conditions. The actual lighting information provides the geometry shadings. Actually, this kind of shading information tells us how the geometries in terms of bond mass or in terms of normals, how this kind of geometries came across the facial regions. Yeah. And in this kind of live view device or this live view systems or light stage, we recover the physically based facial assets. Actually, this kind of physically facial assets includes a diffusion map and also a normal map, and also the specular informations and the bond map, the displacement map. And especially actually we would like to have, because we have the 4D reconstructions, so we would like to recover the topologic consistent geometries. And then we bake this kind of facial PBR assets or this kind of facial textures into the UV space, especially the normal is in the tangent space. Yeah, and because we use the high quality and high FPS cameras, finally we could upscale or upsampling the PBR assets to 8K resolution. And actually, this kind of results are directly captured by the systems. No post-processing. This is the low scan. And here I'm going to show some rendering results using the capture facial assets using available CG rendering pipelines like Blenders or Unreal Engine. Yeah, actually we could see if we if we bake the normal and specular informations with the basic geometries, we could already have very detailed facial geometries. Yeah. And then we could add the diffusion map on top of the diffusion albedos on top of the normals and speculars. Then we could recover the facial geometry details. And then once we add, we could further even add the bump map and change the lighting conditions so that we could relate the facial assets into different environment map. Yeah, and here, and yeah, and because we could actually the whole system, we use video cameras, so we could capture the not only the a single static scans, we could capture a continuous 4D dynamic facial scans, and we not only capture a dynamic performance or dynamic sequence, we also capture how the performance perform different expressions, right? Under different expressions, actually we capture the performance according to the so-called facial accent coding system, FACES. It's widely used in not only academics but also in the facial modeling industry, right? And this kind of FACES corresponds how each of our facial muscles reacts under different kind of expressions. So we capture different human performance under different expressions, and we not only capture the geometries, or we also capture the RGB images, and especially we capture the geometry and the RGB informations under different kind of polarized lighting. So we could have not only the basic geometries, but also have all the physical-based materials like the albedos, normals, bump map, speculars. Yeah. And actually, it's not that easy to build out the whole system, the whole light field stage, and it's also quite difficult to manage it, to scalabilize the data collection pipeline, right? If we could capture efficiently to capture one identity, then we could scale out the whole facial data set. And in our work, we capture a huge available facial data sets. We already capture more than 1,000 identities. For each identities, we provide the topologic consistent 4D geometries, and we bake the geometries into physical-based rendering materials, just as I mentioned before, including the diffusion, normals, speculars, displacement map in the tangent space. And we also capture the performance and the different expressions to fit into the 28 phases. Yeah. And additionally, we provide additional 4D scans because we use the high-speed cameras, so we could capture the dynamic performance of the actors in 30 frames per second. So for each identities, we provide the 5 dynamic performance, which lasts more than 2 minutes to cover all the accent units in the phases. Here I'm going to show one example about our 4D scan. Here on the left is the raw capture images, and then we recover the 4D geometries, and then we bake the geometry, bake the appearance informations into this 4D topologic consistent geometries. And we also not only provides the look deck, but also provides example rendering results on the images. Yeah, on the available CG engines like Unreal. Here we actually please notice the facial geometry details and the facial rendering details, especially near the facial muscles or near the boundary regions about the faces. Yeah, and here we show more results about the rendering examples. And also because we capture the faces, so actually once we have the facial expressions, we could we could disentangle the expression using branch-tree techniques. Actually, because all of these identities share the same geometry topologies, so they natively support branch-tree animation. And this kind of branch-tree animations follows the basic conditions. And so it's very artist-friendly. Yeah, it could be easily embedded into available CG engines, Unity, Unreal, Blender, Maya, yeah, etc. Yeah, and so for each identity, we could already provide the CG-friendly animation renderings. Yeah, but we still would like to go one step further. Yeah, which means if we already have the rich physical-based data for each performance, so maybe we could even try to build a neural physical-based facial assets, right? The target is to provide a video-driven facial assets, which means we would like to use the person-specific data, right? And then we use the data to train a network. Once we train, we want to bake our previous CG facial assets into a network. And then we could use our previous facial animation or use the images encoders to encode the network informations from arbitrary image input or video input, so as to enable video-driven facial animation, facial editing, or facial post-processing. Actually, the key idea is to disentangle all the facial assets into a network. Actually, we use a multi-VAE to model the latent space about the facial assets. And we would like to disentangle the expressions, the geometries, and textures all together based on our previous capture facial assets. Yeah. So actually, this work is done only in last year, and actually it works pretty well. And we even find it could naively enable across cross identity applications. Yeah. For data acquisitions, it's very similar to the data collection that I mentioned before. For each performance, we use 3 high-quality speed cameras to capture the 4D performance. And we also use the parallelized gradients in lightings to reconstruct the actors, not only to reconstruct the actors' facial geometries, but also capture the physical-based textures, all at 24 frames per second, so as to provide sufficient training data. Yeah. Actually, in our neural network representation for the person-specific facial assets, our key idea is to design a multi-VAE to disentangle the geometries, expressions, and physical-based textures in the UV space. And we choose the expressions as the main components because we would like to use the expressions to drive the video assets, right? To drive the facial assets. So basically, in our multi-VAE, we first train a variation autoencoder to learn the global representation for the expressions. So we just encode from the captured multi-view image inputs. We use an encoder to disentangle the expression latents, and then we train the expression latents into the image space. And once trained, we have the variation autoencoders for the expression parameters. And then we further combine these expression parameters with the texture one and the geometry one. Yeah, but all of them share the same encoder, share the same expression encoder. Yeah, so with actually, because we have the multi-view camera systems, so we adopt a novel triplet training scheme, which means we focus on retrieving consistent information across views and frames, so as to enable stabilizations between viewpoints and between different temporal frames. Yeah, and once we train a really good expression VAE, then we disentangle it to the geometry and the textures. The geometry is pretty straightforward, so I just skip it. But for the tetra is quite difficult because we design the tetra networks in the UV space because we capture the 4D geometries and then we bake all the physical based appearance information into the UV tetra, right? So we further design the tetra networks to predict the wrinkle mass or the offset on top of the albedo map. So this kind of wrinkle mass actually models the shading or the blood flow informations according to the motions, according to the expression changes. So our key idea is to model the tetra networks to predict so-called wrinkle mass or bump map. Yeah, and all the wrinkle map represents the diffusion, specular, normal changes according to the expressions. Yeah, once we change our multi-VAE, actually we already have a uniform representation of the expressions. So we could naively infer the geometries, dynamic physical based tetras all at once from an RGB inputs, because we could use the expression lattice to disentangle the geometries, tetras, and the expressions. Yeah. So such physical based facial assets naively enables different kind of downstream applications, such as performance specific neural facial assets to replace traditional brain shake based animations or facial performance captures. And because all our training data about different identities, they share the same topology changes actually. So we thought actually our network could be easily generalized across identity, especially for the expression part. So our physical based facial assets naively supports cross-identity neural retargeting. We could just replace the encoder version, the encoder of the expressions of different identity. So we could use the images or videos about performer A to drive the facial asset of performer B to change its animations, to change its geometries. And another good thing for our physically based tetra is that because we disentangle the geometries and the tetras, so we could naively support geometry and tetra editing. Yeah. Here, I would like to show some demo results.
Introducing the world's first 4D scan with pore level, dynamic, physically based textures.
We can utilize the data in a neural representation of person-specific facial assets to disentangle the geometry, expression, and physically based textures. We can drive our neural physically based facial asset. Our dynamic textures effectively enhance the appearance of the actor. We captured the in the wild videos of other individuals with cell phone cameras. We are able to drive our actors after editing their geometry and textures.
Smile and put on a happy face. She says I was put here to spread joy and laughter.
Thanks for watching.
Yeah, and actually from the first part, I introduced several lighting live field device, and then I introduced how to use this kind of live field device to capture rich facial data to enable different downstream facial animation or capture applications. And some important things goes on. And one actually I inspired a lot from Professor Lee's talk. And actually for human facial modeling, it's very important to combine the outer informations with the inner parametric informations. And actually all kinds of live field device provides rich outer informations, but we still need a lot other observations to provide extra inner of observations. Actually, I think it's quite important to bridge the outer and inner observation for facial modeling, because the outer observation usually related to the appearance information for human face or head regions, right? And such appearance is very important for virtual telepresence or virtual visualizations, especially for future so-called metaverse applications, right? But actually, if we combine more inner informations like the sculptures, the muscles, we could inference the how our human head or how our human face to perform some extra biological or anatomical functions, right? So if we could combine the outer or the inner informations, we could combine the appearance informations with some biological functions about the human head, right? So we try to provide extra informations in additional to the live view device. And we have several attempts. Actually, this way is mentioned by Professor Lee, and this way is called Scouter. Actually, in this work, we try to provide a skeleton consistent facial parametric models. And in this work, we try to not only use the live view device, we also use the inner CT modeling, CT data, CT scans to provide extra information about the parametric skull. And the key idea in this work is to
we start with sculpture's mean face and then sample on
is to combine the inner and outer observations, so we could finally provide diverse human facial attributes, or provide diverse, especially to provide diverse human facial appearance, which is consistent with our inner sculptures or inner traces, right? And actually, as a parametric models,
shape space to add head shape variations.
as a parametric model,
Including
we
trait
have the mean
component
face,
gives
and
the
then we have
subject
the
even more
shape, the
distinct
trace.
characteristics. Then we continue adding facial appearance, pose, and expression
And
parameters
we also have
until
the
we get a
appearance
characteristic
information
face
from the
with a
light
wide
stage.
open mouth. As many prior surface models, we use principal component analysis to create a low-dimensional subspace of shape and trait. As Sculptor jointly models the correlation of skull and face, the outer surface changes accordingly to the inner bone modification. We also model appearance with texture maps. At the core of Sculptor is the Lucy, the first large-scale shape skeleton face dataset. All data come from high-resolution CT scans, taken before and after orthodontic surgery. To include more facial details, we further capture corresponding 3D facial geometry with texture maps.
Yeah, actually, the key idea in Sculptor is a parametric models that combines the skull and face. The skull from the inner CT scanning and the face from the outer light stage, light view stage capture. So finally, actually, it's very similar to previous parametric models like 3D or frame. Yeah, actually, we use the brain shade techniques to model the inner sculptures and the geometries and the outer surface and the outer appearance. And we also try to use additional brain shades to model how the inner sculptures influence the outer surface. Yeah, the key idea actually is to use multi-model dataset, and one from a rich CT scans and one from rich outer light field stage scans. And we just need to combine them into a parametric model, try to build inherently build the connections from the inner components to the outer components. Yeah. And actually, once we have the parametric models, we could have different kind of downstream applications, but not that as we try to not to focus too much from influence the skulls from the facials or influence the outer surface from the skull. Yeah, actually we try to use this kind of skeleton consistent face creation techniques to provide nuanced facial attribute control. Like these examples, we could naively change the skull, change the trace in the skulls, so we could control how the human appearance or how the human facial changes according to the skull changes. And because we have the facial modelings, we could also directly simulate how the ripple changes according to the skull. We could change the ripple levels about the performance to provide different appearance results. And we also try to find some interesting applications behind computer vision or even computer graphics. Yeah, actually, we try to recover the facial appearance information from some partial scouts. Actually, it's very important for archaeological comparison. In these examples,
First, given an incomplete
we try to actually in the EVA, which is excavated in Scotland in 1987, we only discover partial skulls, right? And then artists try to
skull.
scientists could try to
facial appearances with
manually recover the facial reconstructions by using the techniques or even using artists, right? And using our models, we could further inference the outer appearance changes according to the partial skull. We could try to complete the skull first, and then according to different compressions about the skull, try to modularize its outer appearance models.
different mandibles.
Yeah. And actually, we also try to use this outer and inner modeling techniques to model not only the facial regions, not only the skull of the head, we also try to model the head and neck, because actually our neck serves as a connector to connect our head and shoulder, right? And actually, the motion of neck is super important to provide vivid facial animations, especially for some special talkings or swallowing something like drinking. Yeah, and so in this way, we try to modeling the head and neck together, not only from the outer appearance modeling, but also from the inner modeling. But it's quite difficult to capture the CT scans about the neck region. So we use different kind of inner modeling techniques. Actually, we use the ultrasonic to scan the cervical spines about the neck regions, and we also use the normals to capture how our lenses move according to our talkings or according to our appearance modeling. Yeah, we could see the demo first.
We present HACK, a parametric head and neck model. HACK is designed to generate realistic and anatomic-consistent models of the head and neck, allowing for the creation of highly expressive and characterful animations. To sample a new identity, we begin with the model's mean face and add variations of head, neck, and larynx shape, as well as variations in appearance. Then we add parameters for facial expression, pose, larynx position, to create highly expressive models with a wide range of motion. By incorporating identity-related cervical spine joints position, pose, and expression blend shapes, we are able to enhance the distinctiveness of the animations. To train the HACK model, we need a comprehensive dataset. To create the dataset, we use a portable real-time 3D ultrasonic imaging system to capture anatomically accurate positions of the cervical spine relative to the skin of performers in the rest pose using ultrasonic tomography. In addition, we build a plen optic stage to capture static scans of various identities with fax expressions and physically based textures, dynamic performances of the head and neck, and larynx motion through detailed normal sequences. The HACK model can be applied to a variety of applications. First, given a target scan or mesh, we can accurately reconstruct it by fitting HACK parameters. Compared to the state-of-art parametric model, such as Flame, HACK has lower reconstruction error, both in shape and pose registration. We can then manipulate these parameters to create different expressions, poses, and appearances. The identity-related pose and expression blend shapes of HACK enable high fidelity and expressive animations. Additionally, we can infer pose parameters from input head orientation and input expression sequences.
Yeah, the key idea is to use multimodal data to build a consistent head and neck model. Once I have the head model, we could inference the lens motions and the neck motions directly from the partial facial motion capture. In these examples, we use the Apple AR Kit to provide the facial motion capture for actually the brain shape for the head region, for the head region, and then we use a MLP to predict how the lens movements and the neck movement of the performance. And then we combine the head and neck together to provide a vivid appearance models and vivid motions about not only the facial motions, but also the neck and lens motions.
To animate the larynx motion.
Fly me to the moon, let me play.
Here we show the lens vertical versions. Yeah.
What spring is like on Jupiter and Mars.
Hack can even be used to transfer neck animations between subjects, including from a human to a giraffe.
Yeah. Oh, sorry. And
Hack can even be used to
yeah,
transfer
and because actually, because once we have the head and neck models, and we could even perform some motion retargeting or motion transfer. Because, for example, our humans and different kind of animals, actually we share the same cervical spine, so we directly change the motion, change the skeletal motions from humans to the giraffe, for example. And then we could provide pretty realistic motion retargeting.
Animations between subjects, including from a human to a giraffe. Thanks for watching.
Yeah, and finally, I would like to mention a little bit from our recent ongoing work. Actually, I just mentioned we could use different kind of inner and outer device to provide different modeling for the facial regions. And recently, actually, if we have enough data for modeling, and we could even go further from modeling to generation. Actually, we already see a huge success in recently for the 2D multimodal generation, like 2D text-to-image generation, right? And this trends also go into 3D generations for generic objects. And recently, actually in CVPR this year, we already see a lot of fantastic work for 3D generation. Yeah, and I think it also works for 3D facial assets because we already collect different facial scans or different facial assets. And we also have 2D diffusion models to provide vivid 2D image generations. So our key idea is to combine existing 2D image generations with our 3D scans and with our 3D facial assets. So we use the diffusion model to provide test prompt control to customize the facial asset generation step by step.
Expressive facial assets and animations can be a challenging task, but with DreamFace, we have made it simpler. DreamFace is divided into 3 main modules: geometry generation, physically based texture diffusion, and animation empowerment. Our framework allows us to generate
From only text input, we could control the
modern computer graphics rendering.
We could control the geometry. Yeah, and then based on the geometry, we could control the texture map in the UV space using stable diffusion. Actually we use latent stable diffusion. First, we use the clip models or use the LDM to select the geometry attributes and including the hairstyle.
In physically based texture diffusion module, we first transfer the pre-trained stable diffusion to a large-scale texture map.
And then we apply the texture LDM, the latent diffusion models on the physically based texture dataset.
While still maintaining diversity, a prompt learning strategy was designed.
Because actually the texture mask also in the 2D UV space, it shares the very similar texture styles compared to existing text-to-image generator, right? So basically we use the general LDM to provide out of distribution generation ability and we control a tetra LDN to enforce the generation results follows the tetra
As the
pattern.
final step, we apply the physically based texture generator and super resolution module to generate 4-to-blend shape-based map results.
Yeah.
By
So
generating
from a text
physically based
input, we could
textures,
generate
glass
animatable,
surfaces
available,
are realistic
physically based
using modern
tetra
3D
model.
rendering pipelines.
And because we use
Our
the
approach
2D text to
generates
image
facial assets of
generator,
celebrities that
so
capture their personalized
we could
Also,
even generate some really fantastic out of distribution generation ability.
applications.
For example, we could generate some characters from fiction or from some movies or even from cartoons. Yeah, this kind of 2D, this kind of out of distribution abilities actually comes from our scan. We couldn't capture the American characters in our light stage, right? But this kind of generation ability comes from the 2D latent diffusion pre-trained on 2D images. Yeah. So actually, we in a nutshell, we perform the diffusion model in the 3D facial generation. Right? We use the test prompts to control the geometries, to control the texture generations, and then once we have the generation, we could animate it because it's physically based, and then we could even perform further stylizations. And actually, finally, once we have a really good scan, have a really large data set, we could provide generation ability on top of data set, right? And then once we have a generation ability, we could further provide strong reconstruction ability based on our generation, because actually generation and reconstruction are highly related. And I believe Dr. Dean will continue to discuss how we could generate something from our reconstruction pipeline. Actually, the generation and the reconstruction are highly related to enable rich downstream applications. For example, we could, on top of the generation results, we could provide stable diffusions to generate photorealistic images. And we could even do in a different way. We could provide the reconstruction results on top of the cartoon images or even from a single image input. We do not do actual reconstruction, we just do generation, but we conditioning the generation on top of the input images, right? So that the generation works as a strong reconstructor. Yeah, and that's all. I will do a quick summary. In Shanghai Tech, we build different kind of live field device to provide actual outer and inner information for neurohumans, especially for neurofacial assets. Yeah, and then we seek to generation abilities to enable more reconstruction results for neural face. And I would like to thank all of my students and my colleagues, and especially Andy Yu, Professor Andy Yu, to provide all these kind of fantastic ideas. Yeah, and that's almost the end of my talk. And thanks for listening. And yeah. And yeah, and maybe you could take the
Great. Very nice talk. Do we have any questions from the audience? I guess Dr. Shi dropped. See. Then, yeah. Let's see if he can rejoin. And Dr. Dean, do you want to maybe set up
Okay.
slides? Yeah. Yeah, Dr. She just came back. So if we have any question from the audience to Dr. Xu, I guess you can still ask. If not, then yeah, the time is now, it's 10, 12. So, okay, yeah. So maybe, yeah, Dr. Do you want to go ahead and start?
Okay. Okay. So let me start. Hello, everyone. Welcome to this tutorial. It's my honor to have this opportunity to organize this tutorial with Professor Li and Dr. Xu. And next, I will introduce the research progress on speech-driven facial expression generation. The topic aims at generating a speaker's facial video from input speech signal. And I will provide an overview about this topic. And my talk will, along with 4 keywords: problems, challenges, pipelines, and frameworks. And I'd like to describe what problems have been raised and what challenge we have to address, and what pipelines and technical frameworks have been proposed to solve these problems. So we all agree on the importance of natural language and the speech, but I really want to emphasize the significance of facial expressions. The thing is, even before we learn to speak, we can already use facial expressions to convey our emotions. As you can see in this picture, babies can already express surprise before they learn to speak. Babies can express joy and satisfaction, unhappiness and sadness. Facial expressions are not only used to express ourselves, but they also serve as an important channel of communication between people. For example, babies can use facial expression to communicate with their mothers. And babies are very skilled at using facial expression for communication. And babies and children can use facial expression to communicate with their peers. As adults, when we catch up with old friends, we always hope to meet face to face over a cup of coffee or a meal. People have high expectations for communication based on facial expressions in this situation. And how can we obtain facial expressions at a low cost? Researchers have been working on generating facial expressions since the late 1980s, as far as I know. Today, our focus is on speech-driven facial expressions, which is a research direction based on deep learning for generating facial expressions. The basic idea is to input audible speech signals and generate synchronized videos that can be seen. Here is an example from neural voice puppetry. We can observe the generated video from spoken speech inputs.
Makes progress by steps. Most of those steps are small, some are much bigger. Seen from the outside, sometimes people have the impression that, oh, this is a big breakthrough, but no, it's like another breakthrough. But actually, science is very, very progressive. The
Okay, let me stop here. Of course, we can use text signals as input to generate videos. Let me show them.
This is a text-based talking head video with a synthetic speech. You can observe the automatically generated facial expressions, rhythmic head motions, and upper torso movements. Our approach is able to create high-quality videos. We will introduce her work in the following.
Okay. And so, I'd like to talk about what's the difference between the speech and the text signals. And we can discuss this from 2 points. One is their information. Speech signals contain text content and the richer emotional and prosodic information. On the other hand, text has more explicit semantic information, but text has no prosodic information. The other one is that the speech signals introduce timbre information, but the timbre information is a noise signal for speech-generated facial expressions because facial expressions have no relationship with the timbre information. The moving out timbre information relies on amount of data from many processes. It means that speech-driven methods have weak generalization. For example, if the framework is trained on male speech, it is hard to be generalized to female speech. If the framework is trained on human speech, it is hard to be generalized to synthetic speech. On the contrary, text is not specific to any speaker, so a text-driven framework can be generalized to arbitrary process. So according to what we have talked about, speech-driven and text-driven methods have their respective advantages. So I think the use of both will bring more benefits, but it is a still challenge to use both of them. After discussing the choice of input signals, let's talk about the output behavioral modalities. The existing papers can be classified into 3 groups. Some papers focus on the mouth regions, like this. And others focus on the entire full facial expression. Some studies consider the head movements as well as the up torso movements. As observed, we can perceive more natural with more behavioral modalities, of course, with more challenges. And from the perspective of granularity of generated behaviors, earlier works only consider speech inputs. Let me show you.
Who are very happy that I'm making this decision, and I can give you names. I don't want to say it on the air, but I can give you names of them if we have to come back and do that. And the fact is that
let me stop there. And later on, some workers introduce emotional signals. It means emotional labels is taken as additional inputs. Let me show you some more.
Ask me to carry an oily back like that. Don't ask me.
And recent our work has studied style-based. And what does style mean in our paper? Let's first go back to emotion label-driven generation. Emotion label-driven generation emphasizes that the generated facial expression should conform to a certain category. In other words, conform to a specific data distribution. So we call this as distribution data-based. In contrast, we can consider style-based as example-based or instance-based. The effect of style-based generation can be similar to another instance of a specific reference short video. And the style is about maintaining this instance-based similarity. It means that the synthesis granularity can be much thinner. From the perspective of speaker identity, Some works focus on a specific person. These works require several minutes or more of the video data for that person. Generally, the more data there is, the more comprehensive the facial expressions that can be covered, and the better the generation effect. Let me show you an example. This is an example of speak specific. There are also so many works that focus on one-shot imaging, allowing for the generation of videos for any person. Generally, relying on a single person image input poses greater challenges. But many efforts have been made over the years, and the progress has been made. I will talk more about the solutions later. So here, let's take a look example of one shot.
And America doesn't do very well when we can't get along. And I'm disturbed that it's not just, as I say, the ruling class, the elected officials.
Okay. And now we have discussed questions raised by the published work in 4 aspects, including input signals. It can be audio-driven or text-driven. The output behavioral modalities can be only the lip region, full facial expression, and additional head movements, as well as the up torso. And also the topic can involve only speech-based or additional emotion label-based, or even style-based. And the identity can be speak-specific or speaker-independent. And so we have discussed the problems that have been explored in cutting-edge research. Overall, no matter what topic or work, there are 2 challenges to face. First, it is how to align 2 modalities of audio and visual signals. Second, there is a challenge of generating pixel-level high-quality videos. In fact, existing research efforts have focused on addressing these 2 problems. As for the first challenge of audio-visual alignment, of course, we can use animation parameters regression or pixel-level image regression. And moreover, another solution is based on GAN. The series of works by Dr. Zhou proposed to alternate audio and visual signals from different videos in the generator network. Like this, they can make fake audio-visual alignment. So based on the fake and the original real alignments, the framework can fully employ the advantages of GAN. And later on, additionally, I'd like to highlight an interesting work, Wave to Lip, as it is dedicated to building a network for audiovisual synchronization estimator. This is a large different from previous works. Then this estimator is used to supervise the generator to make audio-visual alignment. As for the visual quality, researchers have used several image quality metrics, which are similar to the general image quality estimators, including SCENE, PSNR, CPBD. A recent our work attempts to address another challenge: the diversity of generated video. Indeed, the mapping from speech to video is essentially an one-to-many mapping problem. It means that one audio may correspond to multiple expressions, including multiple mouth shapes, upper facial expressions, and different head motions. And our work proposed to introduce a style from another reference video to generate the video. So different reference videos can make different resulting videos. Of course, I don't think this work have addressed the diversity very well. More efforts need to be made by all of us. Now, let me show you the example.
One of the most important things for me is not only to advance AI, but also to democratize AI.
When we use a different reference video as input to provide the style.
One of the most important things for me is not only to advance AI, but also to democratize AI.
And for the diversity, another solution is proposed also. It introduces additional input video. It means a combination of audio-driven and video-driven. The head and upper facial expressions in the input video can be transferred to the resulting videos. Next, let's discuss the proposed pipelines. And we have discussed the proposed topics and the challenges. And now let's move to pipelines. To address speech-driven facial expression, existing pipelines can be classified into 3 groups. The first group is based on a predefined 3D character model. This work generates only animation parameters to drive match animations. And the second group is the straightforward generation of 2D facial videos at the pixel level. The identity is specified from the video clip or a photo image. And the third group is a kind of the combination of the first two. A 3D face model is first used to generate 3D animation. Then the 3D animation is fed into a neural render and then generate the 2D videos at the pixel level. And the identity information is input to this neural render. By comparing these 3 types, we can clearly see the relevance of each solution. And for 3D application, gaming, and animation industries, the first solution of the model-based 3D parameters generations is suitable, as it only needs to solve the issue of audio-visual synchronization. Its visual quality is left to the 3D engine. If the application is based on the 2D video content, the second solution is more appropriate. This pipeline needs to address both audio-visual synchronization and the visual quality. The third solution can be used for the applications of both, while also addressing audio-visual synchronization and the visual quality. However, these 2 challenges can be addressed in 2 stages. The first stage solves the issue of audio-visual synchronization, while the second stage focuses on the visual quality. And what are the benefits of solving these challenges in 2 stages? It can bring significant advantages. Let's carefully analyze these 2 challenges together. An audio-visual synchronization can be considered unrelated to a specific speaker, while visual quality is specific to a particular speaker. If we can decouple these 2 problems and solve them separately, the modeling of audio-visual synchronization can be shared for any speakers. That means when we want to generate a specific speaker's video, we only need to focus on the second part, while the first part can be shared. This greatly reduces the data requirements and speeds up the application process. And here, let me give an example. It is from our publication at the III 2021. As mentioned above, the orange part is a model of speaker independent, involves generating 3D animation only. It is dedicated to audio-visual alignment. Then this animation generation model can be generalized to actual speakers with a neural rendering, indicated by the green part. Since the orange part has addressed the audio-visual alignments, the green part focuses on the speaker appearance, regardless of audio-visual alignment. So during the video generation, we focus on the green part. So the green part requires a few minutes. In our applications, we find that it would be much better if recording the 40 minutes of speaker-specific video as the training data to training the second part. And here, let me show a few examples. The left one is from our online game, called Justice, where the facial expressions are generated with the 3D animations. Okay, and then these generated 3D animations can be generalized to actual speakers, only requiring a few minutes of speaker videos. It can be, okay, let me show you example. Okay, another example. This is the male appearance, but I use the female TTS as input. Okay, so we can observe the well-synchronized audio-visual alignment. So that's all for now. We have discussed the pipelines that exist based on the different output signals. They are model-based 3D parameters generation, 2D photorealistic video generation, model-based 2D photorealistic video generation. And we have discussed their relationships. And next, let's discuss existing technology frameworks. When we observe the existing papers, they can be divided into 4 groups, categories. The first category is the end-to-end framework, where a network is trained to generate video directly from speech. And the second category is framework based on the 3D facial parameters as intermediate signals, which is the idea mentioned earlier based on a 3D face model. And the third category is based on generating 2D landmark information, and then use this information to guide the video generation. The framework is very similar to the 3D MM-based ones. The basic idea is to generate expression parameters or 2D key points as intermediate signals, which is their common point. However, there are also subtle but important differences between them. The goal of the 3D MM-based method is to obtain facial expression parameters being independent of identity information. On the other hand, the method based on the 2D key point information cannot decouple expression and identity information, which should be carefully taken into account in practice. And the fourth category looks similar to the third one, and it is often referred to as key points based. However, in this case, the key points are not obtained through supervised model detection or from virtual character models. Instead, they are obtained through unsupervised learning, where the algorithm automatically generates some key points, which act as the strongest constraints for the pixel level movements of the entire image. These key points are then used to drive the pixel level generation for the entire image. Like the second and the third categories, the key points act as intermediate signals. However, the difference lies in the source of key points information. Using key points have the advantage of generating a flow field specific to the targeted person. Essentially, this flow field provides stronger constraint for the image and provide better supervision for the generated videos. So it can result higher quality videos. And here, let's go back to end-to-end framework. I'll briefly discuss the development of end-to-end technology frameworks. Some papers aim to build a synchronized audio-visual representation space for video generators. The basic idea is to alternate the audio and the visual channels from different videos. Such alternation creates some fake samples. With fake samples and the original real samples, again, framework can be built to force the generator to produce a video that is synchronized with the input audio. Another interesting work that I mentioned above, that is the wave to live. It aims to learn a discriminator that it can determine whether the audio and the video are synchronized. Another type of work introduces additional video inputs, which provides the movement outside of the mouth movements, including up facial and head postures. And additionally, recently, some works use nerve as the video generator, where the basic idea is to build the mapping from expression, motion parameters to videos. Recently, this year, there has been work using diffusion models as generators. Either the nerve-based or diffusion-based frameworks, they can improve the quality of generated videos due to their capabilities of pixel level generation. And the second framework is based on the 3D face model. The basic idea behind these papers is that the 3D MM-based frameworks allows to obtain expression animation parameters that are independent of identity information, and then use these parameters to generate videos of specific individuals. And the landmark-based framework is similar to the 3D MM-based ones. Some 3D MM-based works first map the 3D expression parameters to the 2D key points, effectively transferring a problem based on a 3D face model to one based on the 2D key points. There are also works based on unsupervised key points that has been validated as effective. When such work comes to our team, then let me show you an example.
And America doesn't do very well when we can't get along. And I'm disturbed that it's not just, as I say, the ruling class, the elected officials.
Okay, and then later on, we improve the approach by focusing the training data on single characters videos to ensure the better audio-visual synchronization. And then we use the unsupervised key points as a media to transfer synchronized expressions to other faces. Let me show you an example.
In this work, we
propose a novel one-shot talking face generation framework by exploring consistent correlations between audio and visual motions from a specific speaker and then transferring audio-driven motion fields to a reference image for talking face generation. The key insight of proposed method is to utilize the advantage of authentic lip movements and rhythmic head motions.
And the basic idea of this work is that the key points based idea guarantee the video quality while maintaining the synchronization based on a specific character's audio-visual alignments. Later on, a work called EAMM introduces upper facial expressions into key points-based frameworks. By incorporating this movement from another arbitrary input video, the quality of upper facial expression synthesis can be further improved. And so far, we have discussed 4 aspects, including problem definition, challenges, process pipelines, and frameworks. The problems involve input signals, output behavioral modalities, synthesis, granularity, speaker identity. The challenges include audio-visual alignments, the visual qualities, and the output diversity. The pipelines have model-based 3D parameters generation, 2D photorealistic video generation, model-based 2D video generation. The frameworks can be end-to-end framework, 3D MM-based, landmark-based, or key points-based. Okay, that's all for my talk. Thank you. So now maybe you have questions.
Great. Any questions? Yeah, I guess if you still have questions after this, then you can send email to either one of us directly. Otherwise, I guess if no more questions, we can end here. Great. Thank you again, everyone. All right. Thanks. Have a good day.
Thank you.
Bye.
Yeah, bye.